Yeah, this
recording.
voice is always dystopian.
Yeah. Yeah, exactly. It sounds like it's reality talking to you, like Big Brother speaking from somewhere.
People on YouTube will have fun looking at this part of it.
Or if you realize you're in the Matrix and you just hear recording in progress from somewhere.
Yeah.
Sure. Yeah. Okay. I guess I'll start since the recording's in progress. All right. So let me. The next thing I want to get to is talking about these particular types of RIP matrices that let you get these fast SIP triple, these support identification triples that we were just talking about in the last hour. That means I need at least a little bit to review the types of RIP matrices that we're going to use for our measurement matrices and our SIP triples, and sort of go through some of that. So I'll do a little bit of stuff which is probably going to be on the boring side for folks who know something about compressive sensing already. So I'll try to do it here. So bounded orthonormal systems. They're orthonormal sets of basis functions. We'll think about it here. That are bounded in the infinity norm over the collection of basis functions. And if you randomly sample from those guys in the right way, you get the restricted isometry property. And everything I'm going to say you can find in Foucault and Rodhoot's compressive sensing book. Mathematical Introduction to Compressive Sensing. Or probably, I imagine, the best cited thing that they have written together on Google. You can find it that way, I'm assuming. All right, so let's get some notation set up. So I'll call one of these basis functions t sub n. It's going to be indexed by a little vector of natural numbers, right? And this is going to be a function on some domain in RD. Could be a product of intervals, probably is in most cases, right? Map into the complex numbers. And so this is going to be a collection of orthonormal functions. Indexed by vectors in, right? We make that capital D, natural numbers to the, producted with themselves D times. And we'll generally look at a finite subset of a spanning basis for some L2 space. So we're going to have a finite collection of these guys that we'll actually care about. So I'll call that B for basis because I'm very creative, right? And I will grab the orthonormal basis functions who are indexed by some n tilde to the d, where I'm using the same bracket notation to mean these are the integers from 0 to n tilde minus 1. And right, so good. So I'm going to have this finite collection. This is going to be the basis that I really care about. And there's going to be a constant k that floats around on occasion, though I'll probably mostly ignore it. So the bounded part of this, part of the name, means that the following quantity is reasonably small, hopefully, or at least not infinite. So I'll call it capital K. This is not a K alpha coherent thing. Erase it from your brain. It's just a number it's going to be the maximum over my basis functions that I care about of the infinity norms of these guys. And it's going to be less than infinity, certainly, and hopefully close to 1. And the Fourier basis, again, which is the most beautiful and well-behaved basis in the universe, apparently it's 1, which is the best that you can do. Right, so that's great. Okay. Excellent. So we need RIP matrices from these bases. So those are going to be formed by sampling a bounded orthonormal basis. So I will just talk about how you do that. So an M by N, and here N is going to be N tilde to the D. So you see what I was struggling with just at the end of the last lecture. I wanted my N to actually be the N tilde that's here now, so that it was sublinear, and I had just screwed up my lecture enough that that wouldn't work. Yay me. So a random sampling matrix of this size is just going to have entries given by random choices of points from the domain of our basis functions, and we're going to sample them randomly according to the orthogonality measure that we have on our basis functions. But you can think Fourier always, and we can just sample uniformly if you want. So they're going to have entries given by random samples. So the L vector n index for our basis function entry is going to be equal to, you take the index that gives you your function, and then you sample it at a random sample, the Lth random sample that you feel like using in your matrix definition. And this is where we have chosen a set of samples. I guess you can even choose them deterministically. I suppose it doesn't have to be random if you really want to get crazy, but they have to be in the domain. That part is good. And these are generally going to be, for best theoretical results, randomly selected with respect to the orthogonality measure of the basis B. So these are the types of matrices and RIP results that we're going to be using for the fast support identification procedure that I'll start talking about in a second. To sort of close the loop on the, so here's something from the book again, of Fukar and Rahut. And there are a bunch of other papers that do this for now more general types of bases. So Simone has a really nice paper that generalizes this actually, and other people have improved the log constants and blah, 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 but you can see the proof in this book. Right. If I properly normalize this random sampling matrix, a random sampling matrix with respect to that same basis, it will have the RIP, the restricted isometry property, so approximately preserve all norms of S-sparse vectors up to distortion given by epsilon with high probability of your choice as soon as, or provided that, maybe I should say, M is sufficiently large. And how large should it be? It should be larger than some absolute constant times this k squared. This is our bounded orthonormality constant k. So exactly this k. So this is our BOS constant k. And now you see why you want it to be small, because if it's quite large, that is not going to be great for you. Times epsilon to the -1/2 times the sparsity times the maximum of some log factors that involve n and s that have been improved since this book. And then you have some dependence that also has to depend on the probability that you want this to actually happen for you. Okay. Right, so good. So I'm going to be working with this basis going forward. It's going to be indexed by vectors now, so I'll probably call them index vectors a lot, whether I want to or not. And if we're doing support identification, we now have to identify, just like in the multidimensional Fourier case yesterday, we have to identify what these index vectors are in order to properly figure out what the support is. So that's sort of our goal, is to figure those out quickly. And we're going to use matrices that look like this in the process. So we're not going to have any weird combinatorial constructions that magically interact with the basis in a nice way. That is too hard for me to figure out for anything beyond Fourier. So we're going to use RIP matrices instead, and connections of RIP results to Monte Carlo integration, basically. That's how this is going to work. Okay. So let's see what that connection is very explicitly. So when we are attempting to learn some function in the span of our basis, as we just defined it, we're going to have a situation then where it's equivalent to learning the coefficient vectors, right, on all of these basis functions. So we want to learn what the C sub this index vector is. So that's what it is to learn this function. So we need to learn the coefficients and the support if it's sparse. And so if we have a situation where this coefficient vector here is sparse, we have a sparse approximation problem, right? So we are using random sampling matrices effectively to try to identify the coefficients on the individual basis functions and what basis functions they're associated with. So we have that. And if we're using RIP matrices that come from random sampling matrices, this is convenient. Very similar actually to what happened last class, because the sampling matrices can be evaluated by sampling, surprisingly enough. Right? RIP measurements are just given by our coefficient vector are just given by evaluations of F. Just want to make this part clear for those who haven't thought about it before. So in particular, right, if I take a random point in the domain of F, it's going to be equal to the inner product of the coefficient vector of this particular function with, well, the complex conjugate of a row from our random sampling matrix, where the row is given, remember, by the particular point that I took here. right? And so this is, each random sample is basically giving me an inner product with a row of our random sampling matrix. So C, inner product of C with a row of our random sampling matrix. Yes. All right. So this is why random sampling matrices and RIP results work out well with this particular type of RIP matrix. Okay, good. The connection to Monte Carlo sampling then, well, what does this mean? That just means that one way of viewing this is that restricted isometry property results are just giving us uniformly accurate Monte Carlo energy estimates, sort of Monte Carlo integration schemes and grids for the class of functions that are sparse in a basis like this, right? So that's effectively what RIP matrices end up doing for us. So let's think about that. RIP matrices will utilize this. Second, give uniformly accurate Monte Carlo energy integration, I should say. Integration grids or points or sparse vectors on a given basis like this, or for sparse or functions that are sparse in a particular basis of this kind. Wonderful. Okay, so I, right, so I have F in the span of this basis, and its coefficient vector, because this is a nice orthonormal basis, it's going to be the same as, so Parseval's inequality type thing is the 2 norm of F, which is integrating over domain S squared dx, whatever, right? And then you want to know whether for some random choice of grid points, this is going to be similar to my little random sampling based estimator for the energy. So these are my random samples that make up my RIP, my random sampling RIP matrix. And so you wonder if this is true, but yes, it's going to turn out to be true because of what we were just talking about before. This is going to be 1 over the square root of m times the set of samples from F. So this is a sampling vector where I have F of y1 to F of yn. And that's exactly the same thing as 1 over the square root of m of my random sampling matrix phi times c. And because this thing because this guy has a restricted isometry property, we know that that's going to be approximately the same as the coefficient energy, and that's the same as, right, so you sort of say that yes, this is going to work. So RIP results tell you basically how to do Monte Carlo energy estimates, and we're going to use that to create our support identification strategy and get uniform bounds by doing it. Okay, so that's sort of what we're going to do next.
Mark, sorry, just a minor thing. So here we are assuming the orthogonality measure to be
How you
the
do your
uniform.
sampling one. Oh, yeah,
right?
yeah, I should be, I should put some other, what do you want to call it? Should put some other,
Or
yeah, anyways.
yeah.
Yeah, you have to integrate with respect to your, so, integrate with respect to measure, orthogonality measure. Yep. Good, yes. Good, any other questions? Anything else? Okay, so this connection, nothing earth shattering, but we're going to use it over and over. So hopefully that is clear. Okay, good. All right. So what I want to do next is I'm going to generate some Monte Carlo type estimators using ideas like this that are going to let us start finding out things about the support of a function that is sparse in one of these types of bases. And that's what we're going to go over next. And because doing it in generality is quite terrible, I'm going to do it with some simpler examples. So we can sort of see how it works. All right, good. Yes. All right. Maybe I will move things over here. All right, so for the sake of simplicity, let me give you a particular function here. So here I'm going to take, let's say, the first entry of my function of many variables and treat it differently. So this is going to be some domain. It could be some interval AB. And this is going to be all the rest of the entries. I'm going to just call them Y. So this will be in some other domain. I'm assuming now implicitly that there is some kind of product basis structure here so that I can separate these domains this way, right? So maybe this is the same interval d-1 or maybe some other intervals, whatever. Okay, so I'm basically assuming that my T sub n n's can be split into separate orthonormal systems on each of these individual portions of the domain. And so let's just say there's some non-zero. This is a polynomial in the first variable P, and I'll have some remaining d-1 integers that define some polynomial on the rest of the basis, right? And maybe it's too sparse, so I'll make my life easier here. Okay. So these Q's are a bounded orthonormal system over this basis. The P's are a bounded orthonormal system over the first coordinate, right? Okay, base domain. Wonderful. Excellent. Okay. So goal one for support identification, which will sort of give away a lot of ideas. I want to find, for this particular example, I want to figure out some way of quickly figuring out what K1 and K2 are. Just these first entries of the vectors that identify the support. All right. So goal one here, I want to find K1 and K2 in n tilde. All right. What are they? What is this much information about the support of this guy? Okay, so how am I going to do this? And I want to do this using few samples, of course. Okay, perfect. So easiest idea, I'm going to just pick some y. I had nothing, no better ideas. And then for all j's in this potentially smaller n tilde set, right? It's much smaller than n tilde to the d, because d could be 100 and this is just 20 or something like that, right? So not too many elements to explore. I am going to compute, what do I want to compute? The integral over, and here I'll just use the uniform measure as the orthogonality measure, so I don't have to write other measures all over the place. All right, you can imagine computing an integral like this. And if I could exactly compute this integral, then what should it be? This is, once I fixed y, this is just a regular old polynomial of one variable. And so this is going to be C1 q sub k1 of y. If j is equal to k1, and it'll be C2 q sub k2 of y if y is equal to k2, and it'll be 0 otherwise. So I run through these n tilde choices of j, and I'm very, as long as these don't happen to be 0, I'll figure out which j's are there, right? Pretty easy. The problem is I can't compute the integral exactly, so I'll do a Monte Carlo estimate of the integral, right? And frankly, if this n tilde isn't too big, I can even pick some xj's that do exactly evaluate this integral. If these are polynomials, I could use some like Gaussian quadrature rule or something if you want.
Sorry, the if, so it's J, the case is over J, right? J
Oh, yeah. Sorry. Thank you. That was an important correction to make. It didn't make much sense there. Right? Exactly. Perfect. So idea is I'm going to use random samples. So I'm going to instead compute 1 over m times the sum L equals 0 to m minus 1 of f of xl of my y times pj xl, right? And if I take like some Gaussian quadrature nodes or something, depending on what p is or whatever, I can do this exactly even, and then I have no errors. So that's pretty easy. So, okay, that seems too easy. What are the potential problems? Well, in practice, there might not be too many problems with that, actually. But if you want to prove something, the real problems are you have to guarantee that you don't actually accidentally get a 0 or something here. And if it's not exactly too sparse, you want to make sure that you're not going to have 0, otherwise you're going to have other stuff showing up, and you want to make sure that the large things still dominate the small things. So you can't just use one y. Using one y is a bad idea. Right? So what do you do instead? So problem 1y is a bad idea. So instead, we'll use several y's. All right, so I'm gonna choose some additional random samples from that other domain and use those with respect to the proper orthogonality measure, etc. Right? Okay. And then, so what do I want? I want each of these for each y. For each individual y, I don't want it to be 0. Let's concentrate on the exactly sparse case. I want the magnitude of this integral or this thing to be large. if I use several samples, it seems like maybe taking the average magnitude for all my choices of y's to be large would be a good idea, or maybe the average magnitude squared, which is going to be nice for analysis purposes. So let's define an estimator that does things that way. So I'm going to test my j in n tilde. And I'm just going to look at the average over all of my random samples of these estimators and try to make sure they're big. I want the biggest ones. So there we go. All right. So I'm going to test this estimator for all j's in bracket n tilde, and I will then take the s largest ones in general, where s is equal to 2 in this particular example. So I'm going to evaluate this guy. For all j and n tilde. If you like, there are better things you can do if you know more about your bases than that's just that they're arbitrary or orthonormal functions, but we can always do this. And then choose the s values of j with the largest estimated value of this estimator. So with E1J largest. Okay, and that is to find what I want. So what I'm going to find are all of the first entries of the support vectors of my true support for this function. That's what I'll identify. So K1 and K2 if the sparsity is 2.
Yeah, what was H? Sorry.
H is us indexing these random samples.
Okay.
So I have M2 of them, and I'm just gonna take these things that should be kind of large whenever I put in the proper J, and I'll average over them. And it's the most intuitive way to describe where this thing came from. And I'll find K1 through Ks, so the proper supports of the first parts of our true support this way. So S is equal to 2 in our example here. And I see I am running woefully short on time. But let me tell you, so let me give you some a lemma that tells you what this actually is estimating for you, and then it might become clear how this is really telling you useful support information. So here's a rough lemma whose proof is actually not that bad. I guess if you want me to go over time, I can prove it without too much trouble. But then I won't be able to tell you how to stitch the estimators together, so we could probably do one or the other. So here's a rough lemma that you can use to sort of understand what these things are telling you. So or some function of the type we're interested in, basically in the span of B. And for some choice of J for our first basis, first element of our basis, first variable, I should say. Let's let C J1, so this is going to be a particular vector, which is going to be a restriction of C. Right, so some vector up here. This guy should be equal, is going to be defined to be equal to this basis vector if the first entry of the index vector is equal to J. Right, so first entry of the index vector equal to J, then I preserve it, and otherwise I zero it out. So just another way of restricting the coefficient vector, because remember how we were doing that last time for the Fourier basis in this funky way here. We want to do the same type of thing. Okay, so if you do that, then this estimator that we defined right here is, and depending on how you set things up, this approximate means up to 1 plus epsilon minus epsilon RIP type condition equal to the 2 norm of this mass vector squared. And so just to point out what that is, right, that's going to be the sum of all the entries of the coefficient vector for our function squared, where the first entry is equal to J. Okay. So if you happen to have a large coefficient where n1 is equal to J, this estimator is going to be big. And it'll say there's something big there. J is something that you want to investigate further. Things should start with J as you continue on in your support identification. That's sort of what this means. So that's how you use it. This is a lot like the bit testing stuff in the noisy case. So E1J will be large if there exists an n tilde and the rest of the variables indexing some other basis functions and the other with respect to the other variables, such that C, J, n prime, or sorry, this should be n prime, is large in magnitude. Right, so something that you want to identify. Okay. The proof is actually not hard. You just look at this thing and realize that if you write fx yn in terms of its representation with respect to the basis, that you end up getting a random sampling matrix popping out, which has the RIP property. And then the approximate orthogonality that we talked about before erases everything the way you want that doesn't have the proper entry in the first place, and then the RIP-ness of the y sub h's preserve the norms of everything that's left, and you're happy. So you prove pretty easily that way. All right. So okay, this tells you something about the support of your function. So in the next 4 minutes or whatever, I'll tell you.
It's actually at the very least 17.
17 minutes.
Yeah, even 20.
20 minutes. Oh
Yeah.
gosh. Okay, fine. I can show you I can maybe write out the proof then. I'm going nuts up here. All right. Okay. So fine. Let's sort of sketch the proof of this because it's not too hard. And then I'll show you how to patch several of these estimators together to get something that you might believe can be shown to be a SIP triple, the support identification property triple. Okay, so proof. We take our estimator, which unfortunately I just erased like a dummy. So I get to write it again. That's how I save time. Could we change to the board where I'm writing? That might help the Zoom audience. I'll let the fact that none of them said that not dissuade me from my foolish belief that they're following. It's okay. I admit there are probably better things to be doing right now. All right, so this is the estimator. Okay, so we are going to expand this guy in terms of the basis that we actually are interested in.
Yep. The second sum is over Steven, or there's an M2. Okay.
Yep.
Yeah.
Thank you. So you pick different, right? Different. They're going to have to be different sizes, certainly in general. So let's expand. We're just going to expand f with respect to our basis and use the product basis structure. So remember, I had the TNs written as products of p's in the first domain that are orthogonal in the first domain and q's that are orthogonal in the next domain. So I'm going to sort of continue doing that using that notation. So here's my estimator. Okay, and I'll expand this guy. But I'm going to break up each one of these in terms of its first entry and some stuff that's left. So n prime, which is the remainder of the index vector in here. So I'm just writing it that way. Right. I'll have my coefficient, and I'll have n1 of x, q, n prime, yh, and I still have pj xl magnitude squared. Okay, great. So this guy has just been expanded into this business. So that is this guy right here. That's all I've done. Great. Now I'll sum over the L's first and say this is these are Gaussian quadrature nodes. So I can do this exactly. It'll kill everything where n1 is not equal to j, right? So I'll kill all of those guys. So if I do that, what I'm going to get, of course, you could do a Monte Carlo estimate or use other RIP properties and then deal with the fact it's not exact, and that's done in the paper and it's hideous. You can do that. So it's either exact or approximately exact, depending on how much pain you want. And we're just summing over the remainder of these n tildes. So, yep, exactly. So this is going to be Cj. So the first coordinate is now fixed to j everywhere. N tilde. So we're in a one dimension down, right? Everything where n1 is in j has been erased effectively. Is the point here. And we have q n prime at yh. Yep, perfect. And so what's going on here? Well, if you take a look at this, if this guy I said was a bounded orthonormal system for the last d-1 variables, right? Conveniently. So I have this product basis structure, so that's going to be guaranteed. And I randomly sampled it. These should be randomly sampled with respect to the orthogonality measure of whatever these guys are. So that's the right way to pick them. And so this is going to be an RIP random sampling matrix. Right, entry. So this guy is an entry of an RIP random sampling matrix. Conveniently enough, And so you can see that what I'm really doing is I sum over this. I can bring this inside. I'll have the square root. And this is really going to be when I sum over all of these entries, this is going to be equal to that RIP matrix times CJ, CJ1, as I defined it above. Where again, right, this is going to be my M2 by N tilde to the D-1 random sampling matrix. And we know because it's has the RIP property that I will approximately preserve this norm up to the 1 plus minus epsilon stuff. And that's it. Really that simple. Okay. If you set things up in this particular way, it turns out to be that easy. All right. So since I was told I still have 15 minutes left, I should still be able to tell you how to patch these things together in a nice way. That's good. All right, maybe I'll, yeah, that's good. Okay, so there's no reason to only find information out about the first entry of the heavy index vectors, right? What did this estimator do? It treated the first entry in a special way by separating it from the remaining D-1 entries, and then did stuff to learn about the first entry of the index vector. You could separate the second entry from all the D-1 others, and the third entry from the D-1 others, and all the, right? Nothing stopping you. So that's the first thing you do. So you quickly generalize this notion. So we are going to use in goal 2, which is to identify all of the entries of all of the support of all of the index vectors in the support in an unstructured way, unfortunately. All entries in the indices where this guy is not 0 if it's in the S sparse case, right? And then when you have noise, you have to do more painful things, but this tells you all of the ideas that you have to follow in order to get that to work. So, right, just to reiterate what I said verbally. So what did this guy say? We could use this for, let's go back to our example. So remember we had, maybe I'll just do a function of 3 variables and make this totally clear, right? So if I have a function that looks like this, and I'm going to need a product basis now because of the way things are about to work out. So polynomials P in the first variable, Q in the second, R in the third, and the non-zero ones are going to be H1, J1, K1. That's the index vector where this thing is non-zero. And maybe I'll give it another term so it has at least 2 terms. Q, J2 of Y, R, J3. What am I doing? That was K. Yes. HJK, HJK, 2 of Z. Thank you. Right, okay. So this is my function, and I want to find all of the proper entries of the index vectors in an unstructured way. So what is my goal? So what does this mean? I want at this stage, I want to find H1, H2, and say, hey, those are entries of my support in the first, is the first entry of the index vectors. And these are the entries in the second part of my support vectors, and these are the entries in the third part. Right, that's my goal now. That's all I want to do. Right, and so how do I do it? So I do it using the strategy that we just discussed up here, where I change this 1 to 1, 2, and 3, and I test all the entries in the first, second, and third variable to look for the large energy estimates that tell me there's a big coefficient where the first entry is H1 or H2, or the second one is J1 and J2, right? So I do this. So we use E1, J, E2, I guess I should, J, maybe I shouldn't be calling them J, E3, J estimators, like that one was about. Do these Monte Carlo estimates that RIP property guarantees to be uniformly accurate, find the information we want. Great. And we've actually learned a lot by doing that, because the true support, right? So what is the true support of this guy? It is these two entries, H1, J1, K1, and HJ, or sorry, H2, J2, K2. Right? These are the index vectors where there's stuff going on that we care about, that we need to approximate this guy well. That's the true support. And it is going to be a subset indeed of all of the product of these three guys that I just found. Right? It's going to be a product of H1, H2 cross J1, J2 cross K1, K2. Perfect. So in some sense, depending on the parameters, how big n tilde is compared to s. If n tilde is quite large compared to s, I've made some progress, because I've just eliminated, I've just reduced the basis where I really have to search to being s to the d, right? I know everything is in this sort of space. So I could stop here and just do an s to the d calculation if d isn't too big. But if d is big, which I'm interested in, like 1,000, then that's still going to destroy me. So I have to do something else. Okay, so the final thing, the final idea to handle that sort of situation is the following. So goal 3, and this is the dimension incremental strategy that I have said we use. That's what we're going to use next. We're going to pair these entries together one at a time. So I'm going to pair the first two together, because then I'll just have a product of two of them that's s squared things. And then I'm going to do an energy estimate to see which of the s squared things has a lot of energy when the prefix starts with each one of the pairs. And then I'll reduce it down to s, because I'll take the s largest of those using an estimator. And then I will take those s things that survive, and I'll pair it with these two and see which of those s squared things again have a lot of energy. And then I'll take the s largest and I'll be done. So I'm going to start figuring out what the true index vectors are by sort of incrementally increasing them by pairing them one at a time with the previous prefixes that I've computed and the next guy whose information I have from this step. So it's a sort of idea. So we're going to pair the discovered entries of our our index vectors together. Incremental in a dimension incremental way. You'll have to believe me that the estimators are effectively identical to the case we had before, except instead of just picking one j, I get to pick a prefix now, and a prefix of variables, and then I treat the remaining d minus that number of variables differently. And I have the same RIP type of guarantees on one side and some sort of orthogonality that I need to get to work out on for the other guys, and things sort of work. All right. So how am I going to do that in this case? So just to sort of give you an idea. So I'm going to take an estimator 1, 2. So I'm going to treat 1 and 2, both of the variables together. And I'm going to pick 2 different indices that I'm going to explore. So one guy for the first entry from this set, and one guy for the second entry from this set. I'm going to use this type of estimator. Right now, I have 2 things to find which 2 of the possible entries that I have here, H2 of the 4 possibilities that I have, H1 and H2, H1 cross J1, J2 are large, have large coefficients in the remaining tail when you let the final coordinate run free. Right? And so if I do this, what I'm going to find, picking the S largest of these S squared possibilities that I explore, is I'm going to find some prefix, which is going to be H1, J1, and H2, J2. These 2 possibilities from those 4 are going to be the ones that I identify. I'm going to do coefficient estimates, and then I'll do an estimator. And then I will attempt to pair these 2 guys. One cross this possibility. There are going to be 4 of these guys. So I'll estimate all of those guys with another estimator. Estimate coefficients in this sort of total set using coefficient estimation to figure out which of the 4 are actually real. So I'll just do a coefficient estimation at this point, right? These are going to be full-fledged three-dimensional index vectors, so I just have to take all 4 of them and do coefficient estimation really, and it'll tell me which ones are actually there and which ones aren't. So in this set of index vectors, and I'll be done. Okay. Great. So in general, then you can sort of look like, or sort of see how many of these estimators you have to use in order to discover support this way. And this sequence of coefficient estimation in each different entry of your index vector, and then pairing is going to be the support identification algorithm that you use in CoSaMP. Right? So all of that Monte Carlo integration stuff goes on in that line 4 of CoSaMP. Spits out a support, you do coefficient estimation, blah, 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 you get back, you do it again to find more support by doing this, and that's how the algorithm actually works. Okay, so that's the strategy. So maybe in the last 2 minutes, we can just sort of write down in a little bit more generality what you do. So in general, what are we doing here? So if we have one of these functions, and Cn is exactly S sparse. We'll just stick to that case. With support. So let's say the support is nj. So they're j vectors. Enumerate them this way, I guess. So what are we going to do? We do the following. So we use D estimators to begin with to recover, and these are exactly those E1J, E2J, etc. estimators to recover the following sets. So I'm going to recover the first entries for all of them in some unstructured mess, and the second entries of all of these guys in some unstructured mess, etc. So now I know what I get to pay attention to, and then what I'm going to do next is I'm going to take the first two and find a prefix of length 2 of the S squared possible prefixes of length 2 that have the most energy, and I'll pick those prefixes to reduce to a set of size S, and then I'll march forward, right? So I'll go ahead like this, doing that, and compare S squared combinations of discovered entries and prefixes. D-1 times, right? So I do the first two, then eventually I have to do D-1 of these sorts of comparisons to build to properly identify in the exactly sparse case the support of the vector. Okay, and so in this sort of support identification strategy, we have these layers of estimators, and the number of estimators we have to use is something like order of D times n tilde. So y is the number of estimators that we evaluate, right? So why? Because I'm going to use all n tilde choices of j, at least in the simplified version. And I have to do that D times. So that's for this first entry, right? And then I don't have to do n tilde anymore. I can do S squared thereafter by just taking these S and looking over the S squared versions, doing S squared estimators. And I'll do those S squared estimators D time, well, D-1 times, but on the order of D times, right? So this tells you why you had the, in the theorem that I quoted before, you had an n tilde showing up, and why you had powers of S. Because if each estimator takes like quadratic and S samples to make sure that it's accurate to get best S term approximation guarantees, you start getting like S to the 4th run times and stuff like that. So I think I am done now. I've exhausted my time and my notes at roughly the same time. So that's it. Yeah. Thanks.
All right, so this concludes our great journey from bit testers to sparse Fourier transforms to boundary orthonormal systems and sublinear-time approximation algorithms in boundary orthonormal systems. So this is the right moment to ask any burning question, final burning question to Mark. Yes.
Can you talk about the relationship between the RAP and the K alpha coherent? Because like in my leading compressive testing, it's like coherence is because like you can't numerically verify whether or not something satisfies the RIP?
Coherence is easier to verify. The RIP is not easy to verify because you effectively have to compute the condition numbers of all n choose s submatrices of a particular size, and it's kind of a nightmare. But yeah, so the relationship is they're fairly closely related. So if you're K alpha coherent, you have a good coherence. You're just a particularly restricted in terms of your entries type of matrix with small inner products between all the columns. So you're going to have the restricted isometry property also because of that. But you're going to have for reduced range of sparsity than what you would like, for example. So you'll be like a sort of worse than you would like RIP matrix. Similarly, if you're an RIP matrix, there are estimates that show that none of your columns can have inner products that are too big. So the sort of inner products of any two columns are going to be bounded by this epsilon type of parameter in the R. So there is a close relationship, but it's lossy. Like incoherent matrices don't make the greatest RIP matrices, or you can't prove that they do anyways. And RIP matrices have some low coherence properties, but maybe not as, not as great as you would like either sometimes, if that helps.
The part that I missed in the lecture was that where was the sublinearity of CoSaMP?
It's so the sublinearity of CoSaMP happens if you can identify supports fast enough in that line 4. So it's the support identification algorithm that has this SIP triple. If it's faster to compute a good support than it is to look through the entire, to enumerate the entire basis and sort of test each one individually, then you get a sublinear-time algorithm, at least per iteration. And so this is an example where if n tilde is big enough and d is big enough, most importantly, if d is big enough, probably, you can imagine doing these estimators and figuring out some decent support faster than the time it would take to enumerate an entire n tilde to the d bit number of basis vectors even once, depending on your parameter settings and how extreme the situation is. And so that's your line 4, doing these estimators to figure out some support. And then you just solve a little least squares problem to do coefficient estimation in CoSaMP, and then you repeat. And if each iteration is sublinear time and you do 10 iterations or whatever, you've got a fast method.
Just a follow-up question, is there any specific reason that, I'm missing that, you're mentioning these results for sublinear, you're actually expanding sublinearity for CoSaMP and not like, for example, OMP. Is there anything specific about CoSaMP?
Not necessarily. The CoSaMP paper is written really well. I have some sort of personal preference for it, I guess, somehow. Otherwise, yeah, you're right. I mean, OMP is it's a similar type of algorithm, right? If you could sublinearize the support identification in OMP, you would have a similar thing happen for you. It's just that the way that the analysis was done, they have really nice modularized analysis in CoSaMP, and one of the things we had to do was to remove their specific support identification thing, throw it out, and put in the generalized condition that would still make all of the analysis work. And that was just easy to do in that particular paper, but I'm sure you could do it in other papers.
Thank you. Anyone online has questions? Ben?
Hey, Mark.
Your baby has a question, or you?
Two attendees.
Yeah, my daughter has a question, and my dog as well. Suppose I had some prior information about where my support is more likely to be. Is there a way you can incorporate this into what you're doing?
Yeah, I guess. So one easy way would be when you're forming these pairs during the pairing step, you could enforce whatever condition hold about the prefixes. So you'd probably have to look over fewer than S squared prefixes, I guess. So you wouldn't estimate stuff that didn't conform to your assumptions about where the support had to be, I suppose, would be the easiest thing that I can think of at the moment. So if you had like a lower set assumption and certain elements of these products weren't obviously going to be lower set compatible, you just wouldn't consider them, and then you would have fewer estimators to do, as one off the top of my head type of suggestion. Another thing you could do, I guess, is well, yeah, I suppose you could do one round of arbitrary support identification to find some unstructured support that looked like it might be important doing this stuff. And then you could say, well, I'm estimating with respect to lower sets, and these things turned out to be big, so I'll just fill in lower sets that contain these things, like the smallest lower sets that contain these, and use that in my next iteration and see what happens. So I guess you could do things that would help you maybe identify the support even faster by incorporating your assumptions. So you wouldn't have to do this every time. You could just maybe probe the support structure a little less often and then use assumptions to fill it out more quickly afterwards or something like that. Those are two very quick ideas, I guess.
I see. Okay. Yeah. Yeah. Cool. That's interesting. I guess from what you said, this is not really something you've looked into yet, right?
Not really. No. Well, yeah. The most I've considered is that you need the random sampling matrices associated with these things. For the theory to hold, you need them to have the restricted isometry property, and you don't want to have many rows, so you need them to have small bounded orthonormality constants, like the capital K. And that means that if you have a product basis of a bunch of, Legendre polynomials where K is equal to 3 even, or something not too bad, some renormalized version, you're going to have a terrible exponentially large D bounded orthonormality constant. So you might want to restrict the product basis in the beginning so that your BOS constants are small enough that you don't die trying to do your Monte Carlo. So that to that extent, we've looked into restricting things just so that you can get the RIP conditions to work out without killing you. So you actually, I mean, to have BOS constants that aren't terrible, in that paper we sort of do some restricting of the bases that we consider so that we can have meaningful dependence on the sorts of constants, I guess, if that makes sense. But beyond that, no.
Yeah, I guess my question was more along the lines of if I have some structure, maybe then I don't need to see the bad BOS constants because I'm always going to deal with that structure where, like a lower set property where you have kind of, so you don't see.
Yeah, so that would be a way to justify having to, that would probably be a way to justify having better sampling bounds, I guess, which might be similar to what I was just describing, because then you can say, hey, well, my BOS sampling constants aren't bad because I'm in a hyperbolic cross, so I don't have to worry about having to sample as much as I thought I might have to in order to preserve these energies while I look for my my heavy coefficients, something like that. So yeah, I think that could also work.
Cool. All right. Well, yeah. Thanks a lot, Mark, and thanks for the lectures. I enjoyed them a lot. So.
Thank you, and hello to to your daughter.
Yeah, Abigail says hello. So.
I remember those days.
All right, so thank you everyone for actively participating to the mini course and making it a very nice experience. First of all, to Mark. So let's thank Mark again. Yeah, see you around Montreal, maybe tomorrow at the seminar, and I'll see you